Hey guys, so we're doing this problem, divide two integers. Let's have a read. Given two integers, dividend and divisor, divide two integers without using multiplication, division and mod operator. Okay, so we cannot use multiplication, division and mod operator. Fair enough. The integer division should truncate towards zero. That's typical integer division. Fair enough. Return the quotient after dividing dividend by divisor. Note, assume we are dealing with an environment that could only store integers within the 32-bit signed integer range. Okay, for this operation, for this problem, the quotient is strictly greater than the max integer value. Return the max integer value. If the quotient is strictly less than this, return this. Okay, so now let's try to see. Firstly, when can this even happen? Both the dividend and divisor are in this range. Now, if the dividend is positive, then if you divide it either by a negative or positive value, its magnitude is going to decrease. Magnitude is never going to increase unless you're dividing by a fraction, which is not the case here. So if you're dividing by an integer, this magnitude is always going to decrease. So can it come out of this range? There is, so for positive there is not no such problem. For there is one case, which is if the dividend is this, then this magnitude cannot be handled in the positive value because positive value is one lesser. So if you divide this by 1, then it's fine because negative can still handle it. But if you divide this by -1, its magnitude becomes 2 raised to the power 31, which cannot be handled in 8 bits. So that's the only case that I can think of where your quotient will come out of this range. And so let's come to the uh, code section, and this condition, let's code it up first off. So if our dividend is value and our divisor is -1, then the answer will be 2 raised to the power 31, but 2 raised to the power 31 cannot be held, so we have to return this, which is all right. So this is done now. So there are two restrictions that have been put on us. One is that, hey, you cannot use these operators, and second is, hey, all the environment that we have cannot have more than 32-bit. So with this, I'm assuming that, hey, I cannot convert this into a long. If I'm given an int, I have to deal with int only. Fair enough. Now I wanna first talk about what is the general approach to solve this, basically to handle the restriction of not able to use these operations. So it says multiplication, division, and mod can't be used, but we can use addition, subtraction then, and other bitwise operators. So let's say if we are dividing 10 by 3, and we know the answer is 3. What we can do, a basic way of division, just look at is subtraction. So 10 by 3 is basically how many times you can remove 3 from 10. You can remove 3 times from 10, and then you will be left with 1. So one of the approach could be that you keep subtracting the divisor from the dividend until the dividend becomes lesser than the divisor. So you have your 10, you subtract 3 once, you get 7. You can still subtract 3. So you subtract it once more, you get 4. Subtract it once more, you'll get 1. Can you subtract any more? No. So how many times did you subtract? I subtracted 3 times. That's how the quotient is. So that could be an approach that would work. But then in that approach, in the worst case, in which case, let's say, and this divisor is 1, I would keep subtracting this. So it sort of becomes, in terms of time complexity, becomes linear. Can I improve this to sort of, instead of just subtracting the divisor one by one, maybe I look for higher values and and then deal with those. So another way that we could do is, instead of just subtracting the divisor one by one, uh, we could subtract some higher value of the divisor, uh, and but we can't multiply. So what we could do is, if you want to make the divisor bigger, or if you want to see how many divisors that I can remove from the dividend, and that how many can come from a left shift operator which will multiply 2 to the divisor. So instead of subtracting just 3, I can subtract 3 and check if that can be removed. I could subtract 2 times 3, I could subtract 4 times 3, I could subtract 8 times 3, 16 times 3, and because I'm now doing this exponentially, overall time complexity would be logarithmic. So in general, 3 is just your divisor, right? So the approach remains sort of similar, but instead of subtracting 3, we would subtract the maximum power of 2 times the divisor that I can remove from the dividend. What that means here is, hey, so from 10, what is the maximum power of 2 times the 3 that I can remove? Right, so here I could remove, um, okay, so this would become what? 3, this would be 6, this would be 12. 12 cannot be removed from 10. So you directly remove 6, right? And it's 2 times. So what you can do is, you'll see, hey, 10 by 3 equals to 2, because you know that you can definitely remove two threes from this, plus, I'm sorry, 4 by 3, and you'll get the quotient out of this, right? Let's take a higher value. Let's do 100 by 3. So that's then you'll see basically, instead of subtracting 3 from 100, keep on subtracting. You're checking lesser values. So we'll do 12, then we'll do 4 times 3 is 12, 8 times 3 is 24, 16 times 3, right? And so on. So you basically, okay, let's cite all the, let's do this. Let's quickly check for 100. So you'll get what? So you'll have 1, 2, 4, 8, 16, 32. And you multiply these by 3, you'll get 3, 6, 12, 24, 16 times 3, 48, 32 times 3 is 96, right? So you only check, uh, so this is the number of iterations that you did. You got 96, right? I mean, 96 is what? 16 times 3. 32 times 3, my bad. So 32 times 3, right? So you go 32 plus, and how much is left? 4. 4 by 3. And then you repeat the same process here and you will get 1. So 33 would be the answer. So that would be our sort of approach to this problem. Okay, fair enough. Now coming back to code it up. First thing you can see is his, it's integer. It can be positive as well as negative. So we want to handle only positive. And before that, there are other cases. Firstly, hey, do we have a divide by 0 error? So we can't have divisor equals to 0. And it just clarifies the divisor cannot be 0. So that is good. So we don't have to handle it. Some other edge cases that we can think of is, or what? So one edge case, a basic edge case is, hey, my divisor is just 1. I mean, probably it can be handled in the code as well, but if divisor is 1, I'll just return dividend. And similarly, okay, that's fine. I was thinking, well, like I can handle if I was thinking if, which is if my divisor is -1, I can just return minus dividend, right? What I'm worried about is this, that on the negative side there is one extra value which is not there on the positive side. And so what if my divisor is this largest negative value? Now it's greater than magnitude with from only it's the greatest magnitude, right? So you could divide anything by this, we'll get 0 only. So can I just return 0? Well, what if the dividend is also the same? In which case you will have to return 1. All other cases we can return 0. Fair enough. Uh, so this is we have handled if the divisor is the main value. Fair enough. Now what I was saying is, let's only deal with positives. So make both dividend and divisor positive, add the quotient, and then we can add the sign later on. Right. So to do that, let's first figure out what the sign would be. So let's say we keep track of sign by saying, hey, is the answer positive? And the way that we can check is hey, if dividend is greater than 0 and divisor is greater than 0, or dividend is less than 0 and divisor is also less than 0, right? So now we know the sign. Once we know the sign, now we can just make both of them positive. So dividend is method absolute of dividend, and so for divisor. Now there's one thing that we have to worry about, which is if the divisor is negative, uh, if the divisor is the maximum negative value positive possible, that we have handled. But what if the dividend is a maximum dividend is this? Then if you do math or absolute, we don't know. We can't that 2 raised to the power 31 cannot be held. So we have to make our dividend smaller. So let's explicitly handle that as well, or rather the magnitude is smaller. So if our dividend is equal to one value, then there are two cases. Divisor could be greater or divisor can be smaller. So what I'm thinking of here doing is so let's think of let's say when we're doing um, minus 8 by 3, right? And in this case I want to make the magnitude smaller than 8 of the dividend, so I basically remove one divisor from it. So I could do it, I could make it uh, minus 8 plus 3 minus 3 by 3, and it becomes essentially minus 5 by 3 minus 8 plus 3 minus 5 by 3 minus 1, right? And if I'm doing minus 8 by minus 3, again the same trick I can apply. I add 2 plus 3 minus 3 by minus 3, and I can see this is equal to minus 5 by 3 plus 1. So I apply the same approach here. So in this case I'll do, so this is this case, so there is a minus 1, and then I do the divide. Now the dividend was minus 8, divisor was 3, so I did dividend minus 8 plus divisor, so and divisor, right? And in this second case this is 1, so I do 1 plus divide. Now how do I get minus 5? So minus 8 minus 3, so minus 8 minus minus 3, right? So here it becomes dividend minus divisor. So by doing this we also handle the case of, hey, what happens to this method absolute if the dividend is greater, because we'll ensure the dividend is not this by removing one divisor from it. Alright, this is good. So now we come back here, we have our dividend and we have our divisor. Now we have to apply this trick, right? So firstly, very basic is we run the loop only till dividend is greater than divisor, right? And let's say the quotient that we're looking for is start with 0. And how do we get this power of 2's? Well, you do basically a single left shift will multiply by 2, correct? Yeah, so basically this is 1, left shifted by 0. This is 1 left shifted once. This is 1 left shifted twice. This is 1 left shifted thrice, and so on. And similarly, when you're getting this, it is 3 left shifted once, and 6 you left shift. Sorry, my bad. If you left don't do any left shift, 3 is 3, and then you get 6, you left shift it once, and you get 12, you left shift it twice, and so on. So these are the two aspects that we'll sort of use here. What we'll do is that shift with track, let's say call it X. Initially we don't shift, so while our dividend is greater than equals to divisor left shifted by X times, then we keep doing X plus plus. And when we come out of it, that means this last X was a bit higher for it. You couldn't basically now. So this X did not work. So the number of shifts that works is X minus 1, right? And so the quotient can be incremented. So we see if this works, that means the quotient was this, right? So it would be 1 left shifted by X times. Now I can make our dividend smaller by subtracting my bad, it should be shift. How many divisors you could remove those divisors, and again start with shift 0. And this is the case where, so for 10 by 3, you could see you could remove 6, you're left with 4. So that, which is what this would do, 10 minus 6. And now we run it 4 and 3, which is why we need this outer loop. Okay, and then based on the sign, if it's positive, just return Q. If it's negative, just return minus Q. Now, are there any more problems here? I can think of one problem, which is when we do this left shift, we only have 32 bits. If we keep doing this left shift, left shift, left shift, left shift, at some point, if it's 0, then it's fine. If it's non-zero value, that means this X has at least one somewhere in its bit, right? And when you keep shifting that 1 to the left, when any 1 comes to the most significant bit, then it becomes negative. And then if you keep shifting, it will even become lesser. And then in that case, dividend would become dividend greater than equal to divisor left shifted by X would be true. And it could be just that it keeps up in a cycle. So what I do want to ensure is I also want to ensure, so basically if you think about uh, just a 3-bit representation, right? Only 3 bits, and including a date consists negative number. So in 3 bits, what is the range that you can have? So in 3 bits you can only represent -4 to 3, right? Now let's say our value was 1. When you left shift once, it becomes 2. But as soon as you left it another time, this becomes -4. And your dividend was greater than 2, but your dividend would definitely be greater than -4. And when you keep left shifted again one more time, now I don't know what happens here. Does it become 0 or does it become 1, right? This is the bit that I am unsure of. So let me, right? So I want to ensure that I remain out of this loop, which is why I add the condition that the thing is, whenever this problem occurs, it will become negative first, whenever this first one hits the MSB. And at that point, I want to say, hey, I don't want to do any more. So, which is if my divisor left shifted by X has to be greater than 0, right? If it's not greater than 0, then that we know that that is the point to break. Okay. So this is another thing to think about. Anything else to think about? Let's do for a 10 by 3. Okay. Dividend is 10, divisor is 3. So we're checking this is fine. So 3 left shifted 0 times is 3. Dividend is greater than 3. You make it 1. So divisor left shifted once is basically 3 times 2, 6. 10 is greater than 6. Then you go one more, 2. So shift it again, 6 times 2, 12. It's not greater. So you break, right? And when you break, you make shift is x was 2 minus 1, 1. So shift is 1. So the quotient becomes 2. And you subtract 2 times 3, 6 from the dividend. So dividend becomes 4. So now we have to deal with 4 by 3. And we'll make x 0 again and we'll get that, and 4 by 3, that's done. So 4 is greater than 3, yes. We come here, 4 is greater than 3, make x 1, which becomes 6. 4 is not greater than 6, so x equals to 1 is not working, so shift 0 was working. Shift 0 means just multiply by 1, that means q plus equals to 1 here. So now from quotient becomes from 2 to 3, and the dividend becomes 4 minus 3, 1. Come out to the outer loop, 1 is not greater than 3, you break. So we have our total quotient is 2 plus 1, which is 3, and we return 3. Let's run it. Okay, let's try and submit it. We got some error. So then just let's run it. Okay, getting an error here. You cannot assign, fair enough. Run code. Okay, let's run other test cases. Alright, this works, and submit. Alright, so it works. So that's the thing. The interesting bit about this problem is the challenges, just repeat the challenges. One was that, hey, you had to deal with 32 bits only, and which is where there was multiple problems. One was this, the integer min value. If the integer min value is divisor, how do you handle? If the integer min value is dividend, then you can't do method absolute on that. So first you make the dividend magnitude smaller, and then this was the bit of which has the core logic, essentially, where we first discussed that you can keep on subtracting the divisor, but then we thought to improve the time efficiency, you check the power of 2's that you could do by left shifts, and then which is what was explained here. Overall time complexity, there are two while loops. Each while loop will run probably, so this is logarithmic, this is logarithmic. So overall complexity is a log of n square sort of. So yeah, so that's the problem.